Okay, again, good morning, everybody. So today, let's consider some more examples from worksheet number 4. Last time, we finished looking at a couple of examples about the arc length, because I guess we used half of the time last time covering some of your questions from previous quizzes or homeworks. So we were able to just finish two arc lengths problem. Maybe we can do a review of that, but arc length is still used in order to find the surface area of surfaces of revolution. So we'll go over more of that in a moment. But let me see. I guess Michael sent well, a good question here, which is basically about the arc length. So maybe let's start with that as a review of what we did last time. Okay. So I hope you guys can see my screen. Okay. Okay. So let me add this example from, or this question from Michael about arc lengths. So let's do it here. Let's call this additional problem. So the question was find the arc length, or find the length of the arc. So I hope by now you are used to my handwriting of the graph of f of x equals hyperbolic cosine of x for x's between 0 and ln of 9. Okay, let me just cut this. And let me put that here. Okay, recall that the formula for the arc length is basically arc length equals the integral from a to b of the square root of 1 plus the derivative squared dx. And analogously, if your function is given in terms of y, then this will just be an integral from c to d of the square root of 1 plus g prime of y quantity squared dy. Okay, so they have both the same forms for the integral with respect to x and with respect to y. But since the function here is given in terms of x, so I'll stick with this formula for the arc length. So and notice that the major component of this formula is the derivative, which needs to be squared later on. Okay, so I'll do that. So if solve for the derivative first, the derivative of hyperbolic cosine is hyperbolic sine. So that reminds us that you need to remember all those formulas from Cal 1 for derivatives and integrals. They will still be helpful for, or they will still be required essentially for for your test number 2, because all topics rely on Cal 2 rely one way or the other on topics from Cal 1. Okay. And then so if I square this, I'll get f prime of x quantity squared. I'll get hyperbolic sine squared of x. So plugging this in into the formula for the arc length. So we're looking for the arc length from 0 to ln 9, okay, because those are your bounds for x. And then root of 1 plus hyperbolic sine squared of x dx. Now, at this current form, it's difficult to do the integration, and u substitution will not work, because if you let u to be the radicand, you will have 2 hyperbolic sine hyperbolic cosine required for the du, so that won't work. So, but maybe a useful thing here to remember is the identity for hyperbolic functions. So recall that hyperbolic cosine squared of x minus hyperbolic sine squared of x is equal to 1. Okay, so that means hyperbolic cosine squared x is equal to 1 plus hyperbolic sine squared of x. All right, do you guys still remember that identity? Because I think that's the easiest way to solve this problem, relying on this identity. Thus, the arc length would be written as the integral of the square root of hyperbolic cosine squared of x dx. And then we just get rid of the square root, okay? And then what's the integral of hyperbolic cosine? The integral of hyperbolic cosine is the hyperbolic sine evaluated from 0 to ln 9. And then this would be hyperbolic sine of ln 9 minus hyperbolic sine of 0, okay? To find the actual numerical answer here, we need to recall, so you see there are several concepts that I need to recall from Cal 1 for this problem. Recall that the hyperbolic sine of x is e to the x minus e to the minus x all over 2. So we have hyperbolic sine of ln 9 is equal to e to the ln 9 minus e to the negative ln 9 all over 2. But look at this, e is followed by ln, so what will remain would be the argument 9, okay? And then for this term, the second term here, I can rewrite it as e to the ln of 9 to the negative 1. Remember, constant multipliers can go up as exponents to the argument of the ln. So that's loss of logarithms for you, another thing that you need to recall for this problem. So the second term will be minus 9 to the negative 1, so that will be 1 over 9 all over 2. Then simplifying this will give us 80 over 9 all over 2. So that's going to be 80 over 18. So that's what? That's 40 over 9. Okay. And hyperbolic sine of 0 will just be e to the 0 minus e to the negative 0 all over 2. That's 1 minus 1 over 2. So that's going to be 0. So therefore, the arc length is equal to 40 over 9 minus 0. So that's 40 over 9 units. All right. Yeah, you see that when I wrote the solution, I used the term recall a lot of times here. So yeah, you might encounter problems like this, especially in the exam, that will require you knowledge about the things from Cal 1. So hopefully you spend some time going over these identities again from Cal 1. But I imagine you will only be dealing with the basic ones, not the more complicated identities from there. Okay. All right. Any further clarification in this? But don't you worry if you are still getting used to using the formula for the arc lengths, because you see later when we do a surface area, we still need we need to evaluate the length of the arc for specific examples. So we will be looking back at that formula or that integrand at least. Okay. Now, if there are no questions, then let's go to surface area. I forgot which comes first, surface area or centroids. I'll go with surface areas first, though they are independent topics, so we can interchange those two. Okay. Now, the idea here is we are forming surfaces of revolution, not solids, because what we'll do here is to consider an arc. Okay. Say this is y equals f of x from over the interval AB. And the idea is we rotate this, arc with respect to some axis of revolution. Say our axis of revolution is here. Okay. And what happens is we get a hollow solid. I mean, we'll form a three-dimensional object, but it would be empty inside. So that's why the volume would be 0 because there is no material inside. So all that we can measure here would be the lateral face of this solid. Okay, and how do we do that? Well, the idea here is look at it as sort of a generalized cylinder. Remember, what will happen is that the formula would be 2 pi radius times height or something like that. Maybe I'll call this length. Or I'll show you why this formula came to be. So first, this the measure of the surface area will rely on the arc length. So basically you will have this, how long is this arc length over here? Okay, so you compute that. But since we are considering surface of revolution, what we'll consider would be a three-dimensional object upon revolution like this. So basically the arc length gets multiplied by how far this curve will travel as you do the revolution. So that means you travel around this circumference of that circle, which depends on the axis of revolution. That's why here you will have 2 pi times r, which is basically the distance traveled by the arc upon revolution, okay? So, and then we sum it up all over all x values, because what I drew here is just a specific value for x. So we do this for all x's from a to b. And then to get the sum of those measurements, we take the integral, because again, integrals are interpreted as continuous sums. So the thing here is you need to remember that the integrand for the surface area is of the form 2 pi r times the length of the arc. Okay, so let's look at some examples here. Let me see if I can pull up our worksheet. Did you had time to look at the worksheet? Do you have any suggestion what number should we answer there? Or any problem you find interesting? Or you were too busy with other things, you were not able to look at it at all? Okay, let me see. Okay, maybe let's go with okay, let's start with problem 24. Yeah, worksheet number 4. So while waiting for your suggestions, I'll just pick a random one. Let's try problem 24 from worksheet number 4. Okay, so for this problem, we need to determine the surface, the area of the surface generated by revolving the curve about the x-axis. So the arc is formed by the graph of f of x equals root of 4 minus x squared over the interval 0, 1. And the axis of revolution is the x-axis. Okay, so let's see this one. So again, if you want to see a picture of this function, well, the full graph of this function is a circle, or this would be the upper semicircle with radius 2 centered at the origin. So what we have when x is equal to 0, we'll have y equals 2. Y is equal to, when x is equal to 1, then x is equal, then y is equal to root 3. Say root 3 is over there. So this is the arc that we are considering, and we want to revolve it around the x-axis. Okay. That's the axis of revolution. Okay. Now, for the surface area, this would be an integral, and then let's use the variable x to take advantage of the function being given in terms of the variable x. So here, remember the formula, we need 2 pi times the radius. The radius is basically how far is a point on the curve from the axis of revolution. So if you look at this, the radius that will be traveled by a point on the curve or a point on the arc would be from here, the AOR, towards this point, okay, which you can interpret as the length of a vertical strip, okay? And what would that be? Well, it would be top minus bottom, right? So the top function is root of 4 minus x squared. minus 0. So that would be our radius. So this pertains to the radius. And then we'll need the arc length, or the integrand for the arc length. It would be the square root of 1 plus the derivative squared dx. And what are the bounds? The bounds would be from 0 to 1, because our arc goes from x equals 0 until x equals 1. Let me just put this over here, because I forgot that we need space for computing the arc of the derivative, right? Because for the arc length, we need the derivative squared. So if we look at this function, then the derivative would be what? The derivative would be 1/2 4 minus x squared to the negative 1/2 times negative 2x. And then let's simplify this before putting it inside the square root. So this would be what? This would be... The 2's will cancel there. So we'll have negative x over root of 4 minus x squared. Okay. And then we'll square this. This will just be x squared over 4 minus x squared. Good. And that's what I'll put inside the formula for the arc length in the integrand. I'll have that. And now I am hoping that this will simplify nicely, because we need to have a good integral over here. So let's try to evaluate this. But after this, will it be fine if I'll just leave the integration to you guys? Though this would be a good review for your exam. So, okay, you'll have root of 4 minus x squared over there. And then let's simplify the second square root. So we'll have 4 minus x squared plus x squared all over 4 minus x squared dx. And so this would be integral from 0 to 1 of 2 pi root of 4 minus x squared. And then I'll split the second radical as a fraction. So if you simplify the top, you will have 4 all over root of 4 minus x squared dx. Okay, and thankfully the square roots will be gone. And what will be left would be integral from 0 to 1 of this will become 2 outside. So we'll have 4 pi dx. And this doesn't look too bad at all. So this would be 4 pi x evaluated from 0 to 1. So this would be 4 pi square units. So this would be the surface area. Okay. Is that good? Looks easy? Now, do you foresee any complication for problems like this? Well, I don't know if you consider axes of revolution that are different from the coordinate axis, because if I'm looking at the textbook, they only covered cases wherein the axis of revolution are either the x or the y axis. But maybe let's play a little bit with this problem and say, what if the AOR is different from the x-axis? Say it's y equals -1, for instance. Okay. Did you consider examples like this in the lecture? Or did you just consider coordinate axis as AORs? Oops, what happened?
On the worksheet, number 25 looks very similar to number 24. It's from 1 to 2 instead of 0 to 1. How would that change? Would the numbers just be from in the integral 1 to 2 instead of 1 to 0, or in reverse? Or will there be some changes?
Yeah, the only change there would be the bounds. You're correct, because you have exactly the same function, but a different x coverage, right? So your x is now run from 1 to 2. So the only difference from problem 24 is that your integral should be evaluated from 1 to 2. No difference in the setup.
All right, thank you. Because I was wondering, since in the other ones we had to change a lot of things, even though the bounds were different. I was just wondering if that was like the same thing for these.
Yeah, you just need to remember that the bounds for the integral actually only depends on the region or the arc that you are considering. So if you see that the arc runs from 1 to 2 instead of 0 to 1, the only change you need to do is change the bounds. Okay. Now it would be a little bit different if what we changed was the axis of revolution. So for instance, in this problem, I am considering the case when the AOR is y equals -1. Okay. So in this particular case, then, okay, we still have all the functions remain the same, except some of the measurements. So here the surface area will still be an integral from 0 to 1 with respect to x. And then you still have the constant 2 pi, but the radius will change because the radius now would be how far is a point on the curve from the axis of revolution. So if you draw that radius, that's going to be from here, until the AOR, okay? So, but again, that is just a vertical strip. And remember, we are measuring vertical strips using our good old formula, top minus bottom. The top function is, what was our equation of square root of 4 minus x squared. The bottom line now is not the x-axis or y equals 0, but it is y equals -1. So we'll have bottom is -1. And so the radius now would be square root of 4 minus x squared plus 1. Okay, that goes here. But the arc length remains the same because the arc length is independent from the axis of revolution. The arc length is simply how long is this curve or the curve that we are revolving. So it doesn't care what is the axis of revolution. So it only care about what is the function that forms the arc. So in this case, we still have 1 plus, oops, let me use red again. What was our function? 1 plus x squared over 4 minus x squared. Okay. Though it might be difficult to evaluate this integral because there is a +1 here. We cannot have the same cancellation that happened earlier. Probably that's one complication here. This might be difficult to integrate. So, but let's just leave it like that. I'm not sure it can be easily integrated. It might not be an elementary form at all. So let's just keep the setup like that. Okay. All right. Any questions with surface areas? Do you want one more example? Let me try, or any suggestion? Are you guys still there? Let me try problem 32 if you don't have any preference over that. Or haven't you encountered any difficult problem about surface areas yet? Okay, you are really quiet today. Okay, let me do this. X equals cosine y. Y goes from 0 to pi over 2, and the AOR is the y-axis. So the graph here is a little bit, well, it is a rotation of the cosine function because we are given x equals cosine y. So let me try to sketch the graph. Though I might be cheating. I will cheat a bit and rotate my tablet when doing that. So when y is equal to 0, what happens? When y is 0, x is equal to 1. When y is pi over 2, cosine of pi over 2 is 0. So I guess the curve will look like that. Because cosine function increases, okay. Pi over 4 is root 2 over 2. All right, so I think that's the graph. And then, all right, and then the axis of revolution is the y-axis. Okay, so now the formula for the surface area is still the integral, but we're doing an integral with respect to y to take advantage of the fact that the function is given in terms of y. Okay, what are the bounds for y? Oh, the problem gave us that. So this would be an integral from 0 to pi over 2, okay, of 2 pi times the radius. Well, the radius would be from here, from the AOR towards, let me use a different color. So from the AOR towards the arc, okay? And you see that that is just a horizontal strip. And remember, when we are measuring horizontal strips, we are just doing right minus left. The right function is cosine y. The left function is 0 because the equation of the y-axis is x equals 0, right? So that means the length of the radius here would be cosine y. Oops. Okay. Times the arc length, right? But remember, the arc length is, or the integrand for the arc length is 1 plus derivative squared. But here we know that g of y is the cosine function. So g prime of y would be negative sine squared y. Okay, you take the derivative with respect to y, so no need for the chain rule here. So, oops, why do I have a square? Okay, that is just sine y. So g prime of y, quantity squared, would be sine squared y. So here we'll have sine squared y. Okay. Now, unfortunately here, I was hoping that something will cancel out here, but it seems to not be the case.
Why don't you use like the rule of the sine to the 2 plus cosine to the 2 equals 1? For the inside 1 plus sine to y.
Come again, what's that? The Pythagorean theorem, remember, says cosine squared y plus sine squared y is equal to 1.
Yeah, you should, maybe you can like remove something from it for the inside and try to make it easier to solve.
Yeah, unfortunately, that won't be the case here. Or maybe 1 plus, it won't be negative sine squared x because remember, the formula for the derivative requires 1 plus derivative squared. So I need to square the derivative. The derivative is negative sine y, okay? If I square both sides, the negative sign will cancel out, will be gone. So that would be sine squared. So in this particular problem, yeah, I cannot use Pythagorean identity, unlike the hyperbolic cosine, which worked perfectly well. But here, the Pythagorean theorem tells us cosine squared y plus sine squared y equals 1. So 1 plus sine squared y will not simplify to anything good. Let's see.
You can do a u sub. You can put the u equals 1 plus sine to the 2 over 2, 1. And that, when you derivative, that should be 2 cos y.
But that would be 2 cosine y times negative sine y. You need to apply the chain rule. Yeah. So that's why that's what I'm also thinking. If I will let u to be equal to 1 plus sine squared y, du would be 2 sine y times derivative of sine y, which is cosine y dy. Okay. Which unfortunately we are losing, or we don't have a sine y in the integral. We only have a cosine there. Let's see. Mhm. If I let u to be equal to sine, let's see if that will work. If I let u to be equal to sine, then du would be cosine y dy, which would be fine. So I will have integral of 2 pi, and then I'll have a du square root of 1 plus u. Okay, but the bounds will change. The bounds would be from 0 to 1 now, right? Because I plug in y equals 0 into u, sine of 0 is 0. Sine of pi over 2 is 1. That's why I got those bounds. But for this one, I will need another u sub. I let w be equal to 1 plus u. So dw will be just du. So this would be an integral of 2 pi times w dw. But the bounds now would be what? The bounds would be if u is equal to 0, w is 1. When when u is equal to 1, w will be 2. So we get this integral. And it is not that complicated as what we saw before. Oh yeah, you're right. Oh, 1 plus u squared. Yeah. And then so this substitution won't work. Du. I'm still stuck with that problem. Well, there is a way to answer this. You can use trigonometric substitution, but that would be for section 8. Probably that's one reason why we will stick to setting up probably most of the integrals we see here, because oftentimes integrals cannot be evaluated using a simple u substitution, and we will meet some of the advanced techniques in chapter 8. I guess here we can do trigonometric substitution. We will let tangent x be equal to 1 plus u squared. Sorry. We will let u be equal to tangent x, but that will be a topic for section 8. So I will defer solving this integral for now. Maybe we can go back here when we learn trigonometric substitution. Because you see, all the substitution techniques that we tried didn't work for this particular problem. So yeah. But the important thing here is I hope you guys understand how the setup is being done, or how we find the integral that will give us the surface area. I guess that's the most important part of this section here. Okay. Yeah, I was just surprised that we cannot solve this straightforward or using u substitution, because this is in the exercises from section 7.5, and the instruction says find a surface area, but this requires an advanced integration technique, which we will learn later, unless I'm missing something. But yeah. Okay, but at least is the setup clear? Hello, guys. You're extremely quiet. Okay.
Are you going to post these later on?
Yes.
Okay, thank you.
Any other question about surface areas? Because I guess this is much easier than volumes. Because all you need to do is, okay, you have a 2 pi, and then determine the radius, but the radius would be the distance from the arc towards the AOR. So all you need to do is to draw a strip from the AOR towards the curve. If it's vertical, then you do top minus bottom. If it's horizontal, you do right minus left. And then times the formula for the arc length, or the integrand for the arc length. So you have square root of 1 plus the derivative squared. And that's all that is to it. All right. Now, if that's okay, then let's try surface. Let's try centroids, finding the centroid. Yeah, I guess Michael is suggesting earlier probably to use a cosine 2y in the identity. Yeah, that would be the du. Du would be cosine 2y, but the problem there is I have a cosine y in the integrand, but I don't have a cosine 2y. Okay, that's why evaluating this would might be much difficult. Okay. All right, so let's try centroids. Well, the centroids is basically some call it the center of mass or the geometric center of a region of constant density. So basically, if you have a region R, bounded by say two curves, y equals f of x and y equals g of x over the interval AB. So this is our region R. Okay, so we will be looking at the geometric center of the region. So the centroid is this point here, which lies in the center. If your object is symmetric or it has a nice regular property, then it would be easy to find the geometric center. But otherwise, we need integrals to compute for that centroid x bar, y bar. So let's call this the centroid. Do you use the same notation in the lecture, x bar, y bar for the centroid?
Yes.
So, okay, good. So what are the formulas for x bar and y bar? How do we compute it? Well, x bar and y bar would be, just remember them to be the central values or the average value of the x and the y components all throughout the region. So the centroid can be interpreted as the weighted average of all x values. So x bar is the weighted average of all x values. Okay, so it is a weighted average. So we divide by the total area. Okay, so we'll be looking at the weighted sum of all the x components divided by the area. Okay, so but we have infinitely many points from A to B. So there are infinitely many x's to take the average of. So we do an integral, because again, integrals are our analog for a continuous summation. So we integrate from A to B. You can think of it as a continuous summation from A to B of x values times the weight. Well, the weight here is the length of a strip passing through that x value. So it would be f of x minus g of x dx. Okay. So you take the x value here, and then you weight it by the length of the strip for that x value. That's how we get the numerator of the integral, and then divide it by the total area to sort of get the average. So this is the central x bar, or the central x value for the region R. Okay. Similarly, you can interpret y to be the central y value. Okay. So again, we divide it by the total area, and then we sum up all y values with the same weight, f of x minus g of x dx. But we will average all the y values over here. But you will notice that there would be a problem if I will simply put y into my formula here, because I am integrating with respect to x, so there could be no y variable in the integral. So I need to have a replacement for y. Okay. So instead of y, what should I use? Well, remember that the centroid is the geometric center of the region. So if I look at this particular x value, what is the y value in the middle of that strip? Any idea?
Wouldn't it just be, well, wouldn't you just square it? So f of x minus gx squared, because it's you want to multiply by y, but since it's in terms of x, you just do f of x minus gx times f of x minus gx. So you just square it.
Close to that, but not quite. Just remember that y bar is the central y value. So if you look at this specific x, because we are integrating with respect to x, so we're summing up for all x values. So if this is my current x value, what is the central y value over this strip? If this is the strip I'm considering, what is the central y value?
It's going to be half of that.
Exactly. That's the midpoint of that strip, right? So you look at what is the y value at the middle of the strip, right? And that is what? That would be the average between f and g, right? So you get f of x plus g of x divided by 2. You take the average of the top function and the bottom function, right? Yeah, that's half of the sum of the two, right? So remember, we take the middle by adding those two together and dividing by 2. Basically, the average between f and g. That's the average y value, okay? Or perhaps you might be more familiar with this form for for y bar. If you multiply this by this, you will have f of x squared minus g of x squared all over 2 dx all over a. Okay, so yeah, you can either do this or do this. They're equivalent. The second one is just simplified version of the first one. All right. Okay, let's look at some examples. So I hope you understand the concept here. So the numerator would just be the weighted sum of the x's, right? And the weight is f of x minus g of x. For y bar, you still use the weight f of x minus g of x, but you take the average y value, which is basically the middle of the two curves, right? So let's look at some examples. Let me see. Okay, let's try problem, what do you think? Let's try problem 36. For region 36, let's find the centroid of the region R bounded by y equals x squared plus 3x, x equals 0, and x equals 3. Okay, so let's sketch the region, though it is not required, but let's see. Just to have a clear visualization of the problem. X squared plus 3x is a parabola with vertex at x equals negative b over 2a. So that's negative of 3 all over 2 times 1. So that's going to be negative 3 halves. So the vertex is at negative 3 halves. If x is 3 halves, then y is equal to negative 3 halves squared plus 3 times negative 3 halves. Okay, so this would be y equals 9/4 minus 9 halves. So this would be negative 9/4. So the vertex is at negative 9/4. Again, my disclaimer, my figure will not be drawn to scale. That's the vertex. and it's a parabola opening to the right. So if x is 0, y is equal to 0. And then when x is equal to 3, what will be x? 9 plus 9, it would be 18. So there you go. Let's see. And then x equals 0. X equals 3. And let's see. I think I need another bounds here. Let's see. I'll add and the x-axis to have a bounded region. So that means this would be our bounded region R. Okay, because if I won't add the condition that the x-axis is also a boundary, then we will have an unbounded region, and I don't want that to happen. All right. So now the centroid. To find the centroid, we need to set up the integral for the area first. So the area of the region, because remember for the formula, the denominators for x bar and y bar involves the area. So the area, I hope you still remember, is an integral from 0 to 3 with respect to x of top minus bottom, right? So since we're using x, we use vertical strips, and for measuring vertical strips, it's going to be top minus bottom. So it's going to be x squared plus 3x minus 0. So we have this. And then we integrate, we'll get x cubed all over 3 plus 3x squared all over 2, evaluated from 0 to 3. That means we'll get 27 over 3 plus 27 over 2. So that's going to be 9 plus 27 over 2, 18. So that would be 45 over 2. Is that right? Okay, I hope I got the correct area. And this goes for the denominator of x bar and y bar. Okay. Now the centroid is at x bar, y bar, where x bar is equal to the integral from a to b. Again, we will be integrating x times the weight, and the weight is f of x minus g of x, which we knew to be x squared plus 3x, right? It's again top minus bottom, so that's x squared plus 3x minus 0 with respect to x all over the area, which is 45 over 2. Oops, I forgot the bounds. The bounds would be from 0 to 3. Let me check. Yes, from 0 to 3. And then that would be the integral of x cubed plus 3x squared dx all over 45 over 2. We're running a little bit out of time, so I'll leave the integration to you guys. I'll just insert it in the version of the worksheet that I will upload later. So you get the constant there. It won't be easy. It won't be hard to integrate that. But again, now let's go to y bar. Y bar is still the same integral, but it would be still over the area, but it would be weighted y values. Well, again, we'll have x squared plus 3x plus 0 this time, all over 2, times x squared plus 3x minus 0 dx, right? Remember, this is f of x minus g of x. This is f of x plus g of x all over 2. Okay. And so if we simplify, it's going to be 2 over 45, integral from 0 to 3. Oh, there would be a over 2 there, so I'll put the 1/2 outside, and then I'll have x squared plus 3x quantity squared dx. All right? So this would be a 1 over 45, the integral from 0 to 3 of x to the 4th plus 6x cubed. plus 9x squared dx. All right, and then I'll leave again the integration, the rest of the solution to you. All right, any questions, guys? Seems that the examples are very easy. Do you agree? Well, I hope you find some time to look over worksheet number 4. But I guess the problems there are quite easy, straightforward, except for the evaluation of the integrals, because I think you might encounter some integrals there, like what we encountered today, that are not integrable using U substitution or using the techniques that we have so far. But don't worry, those integrals will be dealt with in the next section or next chapter, or at least most of them. And that's probably one of the challenges in teaching integrals, because not all integrals are solvable by hand. So that's why I always hesitate to give integration problems out of the blue or impromptu, because not all integrals are solvable by hand. Even if you know all those techniques taught in calculus 2, calculus 3, or even beyond, there are still some functions that are simple if you look at them, but they are not integrable. For instance, e to the x squared. There's no substitution rule that you can use in order to integrate e to the x squared. But come to think of it, e to the x squared is a very simple function, right? So there's still a lot of functions that might look simple, and yeah, they are not too complicated, but they do not have a closed form integral, right? So let me know on Friday what problems do you want to answer from either worksheet 4 or if you encounter some complicated ones from your quizzes or from your homeworks. All right. And we'll also look at Pappus's theorem next time and probably look at some examples for separable differential equations. Okay. So that's it for today, guys. So thank you for coming. See you again on Friday, hopefully with your questions and more participation. All right. Okay. Have a good day, everyone. Bye.